Okay, I think we could start now. Okay, for everyone who's joining today, Happy New Year. And today we are honored to have Yutong He, Kelly, uh, to talk about the joint distillation for flow map model. Kelly is a PhD, fourth year PhD student at CMU, working on generative modeling. And now it's your time.
Yeah. Hi, everyone. Yeah. Thank you so much for having me today. And let me share my screen first. Alrighty. This is the slideshow. All right. So yeah, thanks Tony for the introduction. And hello everyone, my name is Yutong, or you can call me Kelly. Yeah, as Tony has mentioned, I am a PhD student at Carnegie Mellon, and today we're gonna be talking about joint distillation for fast likelihood evaluation and sampling in flow-based models, or what we call it F2D2. Yeah, so let's begin. Uh, this is a collaboration between like many amazing people. That includes our amazing undergrad from Peking University, Xingyue, and she is not here today because she is cursed by her final exam. So let's wish her good luck on that. And we're also collaborating with a lot of amazing professors at CMU. That includes Max, who is sort of like the lead, professor in this paper. And two of my advisors, Russ and Zico, and also Nick and Albert. Okay, so yeah, let's dive right into it. So diffusion models and flow matching are great, as you may have seen on the headline of the news and like also in like many of our daily lives, right? So like diffusions and flow matching research has led to like a lot of great innovations in the past a couple of years, and that includes like fancy like image generating models like Flux from like Black Forest Lab, or like even like language models from Inceptions. And also if you want to do like, I don't know, probably material science, then you will also need diffusion and flow matching knowledge. So yeah, they are amazing. They're great. And a matter of fact, Happy New Year, everyone. This is like the best thing that ever happened to me in 2025. The Italian brain rot, also generated by diffusion, probably models. Yeah, for those of you who don't know, this is just like AI generated like brain rot animals. This guy is called Trararero Trarara. This one is called Bombadiro Cocodilo, and this is my favorite. Tun 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 sahur. Yeah, anyway. Absolutely the best thing that happened to me in 2025. But yet, all of these are thanks to diffusion models and flow matching research. Um, However, at the beginning of time, diffusion model and flow matching are very, very slow at the beginning. I remember when I first started doing diffusion research, which is probably like 2021 or something, it takes like half an hour to generate a 256 or like 10 minute. I would say 10-minute-ish to generate a 256 image. And that's like kind of crazy. And the reason why is because the way that diffusion generates image is by like slowly, gradually, iteratively, like go from like a complete noise to denoise step by step into like a clean image. Or if we like, if you're more familiar with like the stochastic differential equation, formulation, this is basically just like trying to solve an SDE like backwards. So like you need to numerically integrate through this whole SDE, and then it just like takes a really, really long time. But like all research does, someone came to the rescue, and that is the distillation method and flow maps. So at the beginning, there were consistency models, which were basically like try to, well, actually, at the beginning, there was progressive distillation, which was basically just saying that, okay, what if we learn a model that, taking two steps in the new model is equivalent to taking one step in the new model is equivalent to taking two steps in the original model. And then it comes like consistency model, which is like, okay, what if instead of like learning to like gradually denoise, we learn to basically jump to the endpoint from any point of the trajectory. And then there comes like consistency trajectory model, which later on people formulated into flow map, which is basically like instead of like only jumping to the endpoint, we learn to jump from any point to any point along the trajectory. And this is great because if you can like jump from any point to any point in the trajectory, that just means that you can enable like few step sampling along the same like ODE, right? And that's like super nice. The problem is the flow maps or like all of these like distillation models, they only rescue the sampling part. And the likelihood evaluation, unfortunately, for those models are still either completely like impossible or still very, very slow. And to understand why the likelihood is still very slow and how do we fix it, we need to go back in time. Okay. So pun intended, this is also not only that it's like back in time in like real time that like we're going back in the into 2018, we also need to go back in time in the trajectory. But anyway, let me explain. Um, so basically, what's happening is that like you can this diagram is kind of copied from like the one of the authors of the flow matching paper, Jörn Lippmann. But basically, what's happening is that you can sort of like view the family of like genetic models in kind of this kind of category. And like flow matchings and diffusion are all like sort of like grandchildren of like this work, neural ODE, and also continuous normalizing flows. And what is continuous normalizing flows, right? For those of you who are not familiar, like a CNF is basically sort of like an umbrella term that describes a generative model that transports data from an initial distribution, which usually we denote as P0, and that's usually like a Gaussian, to a target distribution, which we denote as P1, and is usually your data distribution, by integrating a ODE that can describe as the following. So it's basically just like you integrate through a velocity, essentially. And the way that you sample is basically you start from some start initial point by sampling from this P0, and then you get an X0, and then you just like, start to like accumulate the instantaneous velocities throughout the trajectory. And if you numerically integrate this, you are able to get a sample. From any point of the of the trajectory essentially. And as you may be able to tell, diffusion model and flow matching all kind of fits this type of formulation. And how does CNF connect to the probability, or how do we calculate the probability from a CNF model? Well, basically, what we sort of describe is that in order for like a CNF model to transport between the two probability distributions smoothly, we need the following assumptions. The first one is what we call the conservation of mass, which is basically like we probability should always add up to one, and it's basically just like there are no new mass and the mass would not disappear during the transportation. And the second assumption is called continuity equation, which basically just says that not only that like the mass or the probability are conserved, which means that they should always add up to one. It should also not teleport, which means that the probability can only move smoothly or like can move like continuously, like throughout this transportation. Um, and basically, this is how we can describe a probability flux. So essentially, a probability flux is what we use to describe the amount of probability flow per unit time through like a unit space. So basically, you can sort of imagine like your probability is like a unit volume water, and like basically the how much that it like goes through, how much water that goes through a unit space per unit time will be equivalent, will be equal to essentially like how fast, or be determined by, I guess, like how fast it flows and which direction that it flows, and also how much like water that it has in the first place. So if you replace water with probability, this is how we get the probability flux. So to give you like a better visualization, I use Gemini or like VO to generate a video. Uh, it actually has sound. Maybe I don't know if the sound is shared, but let's see. Yeah, so basically you can sort of see, yeah, not sure if this is like a good representation, but you can sort of see how like basically the how much like if you see this tank of water as like the total probability which adds up to one, then you can like sort of see how like the probability like basically the amount of probability changes kind of like depends on like how fast and like which direction the water flows, and also like how and how much water it has in the first at that location in the first place. So all right. So essentially, mathematically, we can sort of like write down these two assumptions into this like equation, which is basically just saying that like the partial derivative of the like how of the with respect to time of how your probability distribution changes over time should be equal to the divergence of the product of the probability and the velocity, or the density and the velocity. So, and this, like, the divergence is basically just like a description of like how much probability that outflows from a given location per unit time in every single, like, in every single direction. So mathematically, I missed a negative sign here. I'm so sorry. But basically, this means that because it's an outflow, right? So like how much probability you're gaining is like the negative of divergence, which is basically the sum of like this the trace of the Jacobian essentially. Um, sorry, just the trace of Jacobian. No, and there's no sum. Yeah, so the negative trace Jacobian is basically what the divergence is, and conceptually it means like how much probability that inflows, which is to a given point per unit time from every direction. Okay. So far so good, everyone. Cool. I shall hope so. Uh, and basically, in the original Neuro ODE paper, which was developed by Ricky, absolute legend. But basically, he has this instantaneous change of variable. Like basically, what's happening is that like if you go from this like sort of like almost like definition of our like the probability flux. Then if you do some like calculus exercise here, which I've done for you, uh, then you will be able to get a basically you can go from the partial derivative to a to the total derivative of the log probability, which is equivalent to the divergence of the velocity, of the sampling velocity. And why does this matter? This is actually huge because remember how we sample right from a CNF model. So basically, what we do is we basically just integrate right through this ODE essentially, right? And notice that this log likelihood is also an ODE. It just has a different function here. Then what we can do to calculate the log likelihood at any given PT for any xt is basically just that you first sample your x0, and then as you progress through the sampling trajectory, you also try to solve this other ODE by integrating the appropriate parts. And that's just like amazing, right? And if you want to like calculate the final likelihood, what you can do is you can just like replace t to one and then just integrate from zero to one, or like backward integration of the divergence outflow if you want. So this is like amazing. And another thing, which is like this is like sort of like copied from our paper, which is basically that you can even write it because like the divergence is only like related to x and the v. So v is the velocity, by the way. So what you can do is you can write it in a coupled system of ODE. So you don't need to write them like separate. You can write them like essentially together. And what you can do, you can just like calculate any given data by integrating the flow backwards from x1. Uh, and this is amazing, right? But like, so now we kind of know why flow maps fail to calculate the likelihood fast, right? Because basically, to give a review, like a recap. So what flow map does is basically try to learn to jump from xt to xs by like directly sort of like calculate the displacement as opposed to using the integral. Um, so just to learn to do this jump, essentially. Then what is happening in traditional flow map is that it only learns to jump in the sampling space and completely forget about likelihood because, to calculate the likelihood, you need the instantaneous velocity, right? So when you learn to jump, your model sort of just like you didn't really learn to jump in the divergence or in the likelihood space. And like what you have to do is you still have to calculate the likelihood through solving the instantaneous divergence ODE. Uh, and that just the same as the beginning of the time of like diffusion models where you need to numerically integrate with like 100 or to 1000 steps, right? And that's why it's taking so long. And I didn't mention it here, but like it's actually even more expensive than trying to do like 1000 step sampling because like the divergence calculation is to calculate a Jacobian of like a high dimensional data, right? So that's like super, super expensive, especially without the correct implementation. It's just like way more expensive than just doing four passes of the same model 1000 times. It's actually doing like backward, it's not even backward, it's like Jacobian calculation of of the same model, and that's going to be way more expensive than just doing 1004 passes. Um, so like this is the problem, like that's why flow maps fail to calculate the likelihood of fast. Well, actually, if you think about it, right? The problem is, does it actually fail though? Like, does it actually have to fail? Well, we don't know, right? Because if you think about it, um, to learn the flow map, you basically just like try to learn how to jump along an ODE and just like it just happened that traditionally those ODEs are the sampling ODEs and not like any other ODE, just some like sampling flow, right? But if you think about it, right? Um, to solve for the likelihood, you are also solving an ODE through integration. That means that if sampling is integrating some ODE and to it like you can learn to like directly jump through this integration by learning a flow map, can we also do the same thing for likelihood calculation, right? Because like likelihood is also integrating some ODE, right? I mean like why does it matter which ODE that you're like trying to jump? It shouldn't matter, right? And moreover, remember how we can like write these two ODs in like a coupled system? Then it means that basically if we can learn to jump two separate ODEs, uh, like this system ODE is also like an ODE, right? So you can just sort of imagine like the divergence is just like another dimension in your data, it's like another column in your data, right? Then like then this is just another ODE, right? Then can we learn to jump both the sampling trajectory and the likelihood trajectory together? turns out exactly you can. This is F2D2. Okay, class is over. We done. No, not really. But basically that was the idea of F2D2, which is basically so the goal of F2D2 is try to jointly accelerate both sampling and likelihood in a CNF by learning a joint flow map on the coupled ODE system. Um, so this is just some like more formal definition that I copy from our paper. But basically, just like P0 is some like initial distribution, which is Gaussian, and then like P1 is like your data distribution, and then PT is just the marginal throughout this process, throughout or like what we call the interpolant. And basically, our goal is to design a model such that it can simultaneously achieve fast sampling, which is like you can draw a sample from this trained model using very few neural function evaluations, let's say like under 10. And at the same time, you should be able to do fast likelihood as evaluation as well, which is to be able to evaluate log likelihood of either a model sample or like an offline data sample with very few number of NFEs, which is like let's say 10 as well. How do we do that, right? So let's just like recap what is a flow map or what makes a model a flow map. So essentially a flow, let's say we have the linear parameterization of the flow map, which just means that like let's just assume that we're learning the jump by learning some like sort of like average velocity type of thing where you can sort of just like calculate the displacement by multiplying this average velocity to the like the difference of the time that you want to jump. Okay, so let's assume that you have this parameterization, then a flow map usually you need to fit like two criterias. The first criteria is what we call a tangent condition, which basically just says that like if you are trying to jump from t to t, this should match your instantaneous velocity, right? So yeah, obviously, because otherwise it will not fit the original flow. And then and at the same time, any of the following condition, like one of them should hold. Um, and basically intuitively what is happening is that let's go from the most intuitive one, which is semi-group property. So this thing is basically just saying that if I use my flow map to jump from T to R, and then I take a break, and then from R to S, like my the XS that I ended up at should be the same as when I directly jump from T to S. So this is just like basically just saying that like using the same flow map to jump one step should equivalent to jumping two steps where you take a break in the middle. Um, and there are also two other sort of like conditions. The first one is what we call like a Lagrangian equation. This is sort of just like you kind of like just like try to like imagine like you're following like a particular sample or like a particular particle in your water flow, right? And basically what you're saying is that if I follow the same particle through this flow map and I jump from S to T, then when I jump to S, like the instantaneous flow that I should observe at the at time s should be equivalent to basically like to the derivative that you take through x. So this is basically so you can sort of like see like Lagrangian as like you are following a particle in the water, so to speak, or following a leaf, I guess, in the water. And then the leaf should be the same leaf. It should be like consistent, essentially. And then the Eulerian like equation on the other hand was basically to say that like okay, so if I'm standing on the bridge and then I'm looking at the water should be the same water. This is kind of abstract, but basically what we're saying is that like if you will end up like basically given some xt like if you will end up as some XS, like when you jump to X, then like basically no matter like if you like just like no matter which XT you come from, like basically you can either come from like XT, you can come from XT1, you can come from XT2, as long as it's like on the same trajectory, like on the same flow trajectory. Like no matter which T you pick, you should end up at the same XS always, sort of, because you're following the same flow. So this is kind of what it means. So, yeah, like it's a little bit like it's a little bit abstract, I would say, that the other two, the Lagrangian and the Eulerian, but um, all it's saying is basically that like if you satisfy any of the following conditions, your flow map should be a correct jump that can recover the displacement that would have happened if you integrate the original instantaneous flow. Yeah, so basically, this is like pretty much the only thing that you need to remember. Um, okay, and all right, so now that we have like a like sort of like a basic criteria of what is a flow map, we can sort of characterize what is a F2D2 joint flow map, right? So the idea is like really simple. Basically, you just kind of need to like properly define your ODE and then try to like make your OD or try to make your flow map, you know, match the flow map criteria that belongs to this like ODE essentially. So what we do is we will have two sort of equations that characterize the displacements or like the jumps of both the sampling path and the likelihood path. The sampling path will be denoted by U, and then the likelihood path will be denoted by D because divergence. And essentially, what you can do is you can essentially write everything like what we write the coupled ODE system. So what you do is you basically just say, okay, like to match this coupled ODE, you will also want to have a coupled flow map, which is literally just like jumping along the flow map is to jump both in the correctly in the both in the sampling trajectory and in the likelihood trajectory. And because they're coupled, it can be you can jump together. And we also denote like basically sort of like the instantaneous flow and divergence with like another function just for the sake of like notation simplicity. And once we have this joint flow map, we like this joint flow map should fit again the two criterias that we just mentioned, which is basically the first one is the tangent condition. Um, when you try to infinitesimally jump, you should be able to recover both the instantaneous velocity and the instantaneous divergence. Um, and the other thing is obviously, other than that, other than fitting the tangent condition, you should also fit one of the following conditions. You either have semi-group property, which means that you jump, like you jump like making two jumps is the same as making one jump on the same trajectory, or you either preserve the same particle trajectory, or you preserve the entire flow, essentially. um so this is kind of like the idea. How do we train? We're gonna give like a more intuitive, algorithm later, but let's just like take a look at the overview of like how we should be able to train a F2D2 model. Um, so basically, a typical F2D2 loss will come in four parts. It look like a lot, but it's everything makes sense actually. So the first loss is what we call the velocity matching loss, which is basically just to ensure that the tangent condition holds for the sampling ODE. And then there should be a like a like a sort of like a flow map loss, let's just say like a or like a sampling flow map loss, which is make sure that one of the three flow map conditions holds for the sampling path. And similarly, for the likelihood path, we need to make sure that the tangent condition holds and also one of the three of the flow map condition holds. So like if you separate them into two groups, so the first group is basically just to make sure that it's a valid flow map for sampling, and then the second group is basically to make sure that it's a valid flow map for likelihood. And once we have this sort of like generic recipe to train an F2D2 model, we can now see like basically how we can adapt the existing sort of like flow map algorithm into training an F2D2 model. So the first instantiation we're gonna be looking at is a flow is sorry it's the shortcut model. Shortcut model is like sort of like became kind of popular like as soon as it was out there. Actually, I think it got viral on Twitter because it got like all A scores or like perfect score or something on iClear. But yeah, it's like insane. But what is happening here in shortcut model is that basically they sort of separate their training into two parts. So the first part is like you do normal flow matching on your data. So this is basically just to say that we want to make sure that the tangent condition holds for sampling. And then the second part is basically to say, okay, so if I take basically this is just to say that like if I take one small step and then take follow the OD and take another small step, this should be equivalent to directly taking one big step. That is equivalent to twice the size of the step size. So this is actually pretty much exactly semi-group property. It's like sort of like a weaker version, I guess, of the semi-group property. It's like more similar to like midpoint solver. But yeah, but basically this is just to make sure that the trained model satisfies the semi-group property. For this shouldn't be likelihood, sorry, this should be sampling. Um, but yeah, this is basically what's happening in shortcut model. Um, And in order to adapt a shortcut algorithm in to train a F2D2 model, all you need to do is literally copy the two losses that you see in the previous slides to train your velocity head, to train your like sampling head, and then you basically just like do the same thing, but instead of like trying to match the velocity in the sampling, you try to match the divergence. And similarly, jumping along the likelihood path or likelihood trajectory, you do midpoint jumping is the same as doing like a large jumping. So that's pretty much that. And what's good about this is that like and we're gonna be talking about it later in the when we talk about the practical design choices, is that you can actually just directly sort of like initialize your model with a pre-trained shortcut model, and then just do sort of do F2D2 fine tuning with like one additional small head at the end, and both of the head can be sharing the backbones. Okay, so yeah, so that's shortcut model. Another instantiation that we're going to be looking at here is mean flow. So mean flow is again another super popular uh, like one-step models that just like that got out there last year. But basically the idea of mean flow is that like you're trying to sort of like learn a model that predicts the average velocity of your trajectory. And the way that they do it is by enforcing this like mean flow identity. So there's some like algebra here or like I guess calculus here, and then you're gonna get like the average velocity is equivalent to instantaneous velocity minus like the time displacement times the time derivative of your like average velocity model. Um, And so we proved that in our paper. Um, Somehow this is like the first time that anyone is proving it. Unclear why, but this is like the first time that anyone has shown that like mean flow is a Eulerian flow map. What it means is basically it fits both the tangent condition and also the Eulerian equation. Why is because let's copy over the mean flow identity. You may notice that there's a sign change here. Before it was minus, here it's plus, and the reason why is because the mean flow paper was written in the same convention as diffusion models, which means that time zero is the data distribution and time one is the noise distribution. And in our paper, we write it in the flow matching convention, which time zero is the source noise distribution and time one is the data distribution. So that's why we have a sign flip here, but it's the same thing. But basically, this is the mean flow identity. If you do some, calculus, you will get this. This is actually what they use in their training as well, in the mean flow paper. So basically, this is like how you basically you have a JVP here, which makes everything easier to compute in PyTorch and JAX, and you do further, algebra. And you do further algebra, sorry, not algebra, calculus, and then you do further algebra, then you're gonna get your Eulerian equation back, basically. Yeah, so it's pretty simple, but yeah, but this is why mean flow is actually a Eulerian flow map. So what Odd is saying is that enforcing the mean flow identity is equivalent to enforcing the actually both the Eulerian equation and the tangent condition, because if you take t to s or s to t, uh, then you're like this whole thing gets canceled out, and then basically just t is equal to the instantaneous velocity. So yeah, this should be S. Sorry. Many mistakes in this slide. Very bad. Um, but yeah, so this is why mean flow is a Eulerian flow map. Cool. So now that we understand what mean flow is, we can adapt it to the F2D2 like fine tuning essentially. And what you do is because the original mean flow objective uh, sort of like encompass the both the Eulerian condition and the tangent condition. So you only need two parts here. And the first part is the original mean flow identity, or the mean flow loss. And then the second one is the divergence mean flow loss. And if you like, so this part basically, you like feel free to look at our paper to see the full derivation. But basically, if you do enough calculus, you're gonna get something like this, where like you're actually the JVP here is to multiply the velocity instead of the divergence. But yeah, but this is like how you're supposed to do it through correct calculus, I hope. Yeah, there were a lot of calculus practice in this paper. But yeah, anyway, so basically the first part is to make sure that it is a valid flow map for the sampling and then sampling trajectories, or sampling ODE, and then the second part is to make sure that it is a valid flow map for the uh, for the likelihood trajectory. Okay, amazing. Um, so now that we have gone through two examples of like how we can adapt F2D2 to existing flow map method, we actually also because we have essentially one step, right? We could do one step by jumping directly from zero to one, likelihood evaluation. We actually are able to do something that is like pretty cool. That can just sort of like give you better, image quality or sampling quality for free, essentially. And what we did is we what we call a maximum likelihood self-guidance. And what you do here is basically you first sort of like calculate the forward likelihood. So you remember how you can like with a given with the offline data, you need to like do backward integration of the likelihood trajectory. But if you are sampling you are sampling, then like you can simultaneously get the likelihood for this generated sample. So we just do forward integration of the same ODE for likelihood. And but because we can directly jump the entire integration, so the likelihood just became like the base or like the source log likelihood divided by the sorry, not divided by minus the um the displacement that we predict from our model. And you can sort of do some like atom or just any honestly optimization to get sort of like a good x0 or like a good starting point in your source distribution. And then you just do normal sampling, and then eventually you may be able to get better samples from this like simple maximum likelihood self-guidance sampling algorithm. So yeah, so speaking of, try to implement things, like there as with like a lot of, the papers, um, there are certain like practical design choices that you kind of need to take care of when you're trying to actually adapt your theory into practice. And so here we sort of list out a bunch of things that you should keep in mind if you are trying to use F2D2. So the first thing is parameter sharing. Basically, because the sampling prediction, the sampling path and the divergence path, they sort of both share the same underlying dynamic, if you will. So it's actually like a good idea to basically just have them share the same backbone. So this is like obviously you could train two separate models. That's totally fine. But sharing the same backbone will essentially just give you fewer parameters that you have to train. And that's totally doable. And that's what we did in practice. And then the second thing is Hutchinson trace estimator. Basically, what's happening is that like the calculation of the divergence is super expensive because it's a calculation of the Jacobian and then you take the trace of the Jacobian, right? So it's like the Jacobian calculation itself is like not super optimized by the deep learning framework essentially. So what we do is we follow the conventions that used in like the origin like the original paper that discovered this trick, and also flow matching, and also the score SDE paper. So what they did is basically they just used a Hutchinson trace estimator. What essentially is saying is like in expectation, this thing is is unbiased. It's the same as like you directly calculate the trace. So basically, just like sample a small like noise vector, and then you just and then here you can just do two JVPs essentially. Like Jacobian vector product, and that thing is much much faster to compute than computing the trace of a Jacobian. And this thing, yeah, is unbiased at training time, so this is like great news for us. And we only need to, by the way, we only need to calculate the divergence for the training supervision. We don't need to calculate divergence like anytime at inference time, essentially. And the third thing, which is like a pretty interesting thing that we actually do not have full explanation to it. But basically, what's happening is that um, all the existing flow maps or like they only deal with sampling. The task is sampling, which just means that they only need to take care of the forward integration of the ODE, and they never needed to go back. And because they never cared about likelihood. So this actually is problematic. Like this may or may not be problematic. Actually, basically, if you only need to evaluate the likelihood for the samples that you generate from the same model, then you're fine. Then you're totally okay with just doing forward only training. But if you want to evaluate the likelihood for any of the collected samples, right? Any of the things that already existed that is not generative by your model, then you want to be able to integrate backwards. And like I said before, right? Like basically you should be able to like if you directly adapt like the four only training, it may have a problem. But it turns out that basically we found that a very simple first order estimation from the four only trained model works super well already in practice. So this is really good news. It means that basically all the tricks that people have developed for the four only training that includes like how to like what kind of distribution that you should sample your TNS, which is crazy basically. Like people tune like spend so much time tuning this thing. Like they like it's a larger normal distribution with really weird parameters, and like you also need to like make sure that the ratio of like flow matching only training and like it jump like the flow map training needs to be like proportional to a certain like ratio. It's like really crazy thing that people like tune for the four only training. Oh yeah, and also like the time embedding that people use in the models is like if you do not use a certain thing, it's not stable. And like those things are only tuned for four only training. And we found that actually just a very simple for first order estimation with the four only trained model works well enough in practice. That just means that you can just use it, use all the tricks, and that's totally fine. Although obviously, like it probably be better if you do forward backward training. But in our experiment, we actually only do forward only training. Um, and speaking of like, warm starting with pre-trained models, like basically because divergence benefits from accurate velocity, it it be like really beneficial if you first only train the sampling flow map, like just do a regular flow map training, and then use the same parameter to warm start the joint flow map. This is like what we found in practice, like super helpful and stabilize the training. And another thing to note is that basically, if you are doing warm starting, or like what you can even do further is that you can first pre-train a flow matching model and then use it to warm start the sampling flow map and then use that to warm start the joint flow map. And if you are doing that, it's actually better for you to not do flow matching or not to match to the ground truth flow, but to match to the teacher flow, which just means that you should just do L2 loss on your instantaneous velocity from your flow map versus the flow matching model and not the x1 minus x0 thing anymore. So we found that this also has like very good performance or better performance than than doing like non-stage training. And basically based on these two observations, we sort of proposed like a small um, like deviant or like a small variation to the shortcut algorithm. So what you do is you literally just what I described. You first train a flow matching model, and then you warm start your shortcut model, just sampling only shortcut model using the flow matching teacher, and also replace the flow matching loss with teacher matching loss in there. And then you use this shortcut model to warm start the joint flow map training and just fine tune it with the F2D2 loss. And again, replacing the flow matching loss in the original shortcut model with the teacher matching loss. And if you do that, um, well, let's look at like a more simple example first. So if you do all of that, then what you can do we can see is basically so this is like the 2D checkerboard distribution, and we can see it's like basically if you are doing like just normal flow matching evaluation of likelihood with only one step or four step, they're not super accurate. Actually, one step is basically just like breaks, but with shortcut F2D2 you're actually able to get very accurate likelihood estimation using one step or four steps. Uh, Moreover, obviously we need to apply this to a more realistic data set, and then we tried it on CFAR 10. So basically what you can observe here is that all the previous models, whether it's flow matching or all of these sampling only flow map models, they do great on FIDs, which means that they do great on sampling. But if you use the but if, in order to calculate the likelihood, you still need to take the divergence of the instantaneous velocities in each of these models. And flow map model also has instantaneous velocities, right? It's just UXT TT, right? So you still have to do that. And like if you like because it's instantaneous divergence, so it's not like very like it's not going to be accurate if you just do very few step numerical integration. But unlike those models, our model can do well both in estimating the likelihood as well as doing sampling. So like the FIDs that we get is like not bad at all. Actually, mm, a lot of the times they actually well only one time I guess they actually improves upon the original uh, uh, sampling only shortcome flow map models. And like another thing that we demonstrate is that the maximum likelihood self-guidance sampling is able to like basically if we do that is able to surpass not only the original sampling only flow map but also the FD2, F2D2 fine-tuned flow map, and also like flow matching models with 1,000 steps. And basically, this is like a three forward passes plus like one backward pass, essentially. And that's like huge. That just like saves huge amount of time. Uh, and we also tried it on ImageNet. We didn't really do MinFlow in this case because MinFlow didn't have pre-trained checkpoints for ImageNet 64 by 64, and our budget only allows us to train 64 by 64, unfortunately. But yeah, but we're looking at adding another set of experiments to add another data set perhaps in the future. But yeah, so this is like pretty much everything for this presentation. If you're interested in our paper, feel free to check out the QR code. These are links to both the paper and the code. Yeah, and thank you so much for joining today.
Yeah. Thank you very much for the talk. Does anyone have any questions? Uh, Maybe I will raise my questions first. Yeah, my question is like, so during training, so essentially you are moving the trace estimation, the Jacobian, the JVP from the sampling time to your training time. So I'm wondering like how many additional overhead you need to train on with this additional JVP in your training objective.
Yeah, that's a great question. It's actually not that much because we warm start the model with like the original like sampling flow map, or you can just take a pre-trained model, which is what we did for everything actually, especially for MinFlow. We just like took their pre-trained model checkpoint. So like the usually the sampling only flow map would take like about say like 2 days to train. The F2D2 fine tuning only takes like 5 hours or 5 to 12 hours. It's like not that bad at all. Yeah.
I see.
But yeah, I agree that essentially the trace estimation or like the calculation of the divergence is like really expensive, and for certain tasks that is not so high dimensional, it might be a good idea to use the true divergence, but because like images are very high dimensional, so we use the Hutchinson estimator. Yeah.
Yep. And and the other question is, I think the Hutchinson estimator, although it is unbiased, but it can be very inaccurate in high dimensions.
Yeah.
So I'm wondering, like, because you are now moving the Hutchinson into your training, So you are
Mhm.
training, you're regressing with an unbiased estimator.
Yeah.
I'm curious if it could also help improve the accuracy of the trace estimation.
Yeah, yeah, it would definitely improve, like guarantee. Like basically, yeah, Hutchinson estimator is one source of error, I would say. And although it's unbiased, so like technically it should be fine if you train for long enough. But it's yeah, I agree that like if you are able to have a better divergence calculation at training time, it's definitely gonna improve the performance. Yeah. But this is just a more like I guess realistic design choices that we had due to our budget.
I see.
Yeah.
All right.
Yeah. Thank you so much for the question. Anyone else?
Hi, I had a question.
Yeah.
A great talk. I was wondering, you talked about using self-guidance. I was wondering if this method could be useful or other types of guidance, like classifier guidance or classifier-free guidance, or some of these training-free guidance methods could be integrated into your method.
That is a great question. And I think it so it depends. I believe that classifier free guidance should be able to integrate it for the original like sampling only flow maps. However, the the meaning of like yeah, the meaning of classifier free guidance can be a little bit iffy if you try to apply it for the likelihood only for the likelihood path essentially, right? Because like it now it's sort of like you are taking you're sort of trying to estimate your like displacement by like basically you're saying that the displacement should come from like two weighted sources and it could be like basically it could be a little bit iffy and it may break some of the like it can potentially break some of the properties for probability. But that being said, I think uh in practice it may it may still be useful. We have not tried it. Everything we did was unconditional. Oh yeah, and that's why the ImageNet numbers are slightly higher than you may expect, is because it's unconditional ImageNet. But yeah, everything we did was unconditional, so we did not really try classifier free guidance. But yeah, but it would absolutely be interesting to try it if there's a setting where conditional likelihood makes sense. Yeah.
Okay, thank you. I was a quick follow-up. Do you think this could be applicable with like a gradient guidance or like classifier-based guidance, or even some
I
of the
see.
more inference time methods? I know there was like a recent like inference time method with flow maps.
Yeah, yeah, yeah. I think this is like definitely, right? Like so basically this thing here is literally just inference time guidance in flow maps, right? I guess this is like different from like the diffusion posterior sampling type of thing where you try to like change the trajectory. Here you are kind of like try to do basically sort of like initial you're trying to find like a good point to sample from your initial source distribution. So yeah, I think definitely. So basically, you don't need to have this NLL here, right? Like you don't need to like maximize the likelihood. You could be maximizing likelihood times you like this likelihood could be like basically likelihood times like another probability from like a classifier, right? Or like likelihood times reward, some kind of reward. Definitely possible, I think. Yeah, yeah, but like um I would say, yeah, so if there's any like loss functions that you are, that you're looking into that has like a likelihood, like a log likelihood portion in it, yeah, I think this should be applicable. So one follow-up work that we are like actively doing right now is try to basically try to do like a reward, sort of like a reward guidance, or more of like a like a RL type of setting where you have a reward function, and then you try to we're trying to make this fine tuning online essentially, and see if it's gonna work. But yeah, we don't know if it's gonna work yet. It's still in progress. But yeah, definitely doable. Yeah.
Thank you.
Yeah, thanks for the question.
Okay, I think maybe we could call it, right?
Okay. Yeah. Thanks
Yeah,
everyone.
thanks, Kelly. Yeah, thanks for joining.
Yep.
Yeah, see you.
Yeah. Bye
Bye
bye.
bye.